Hello viewer. Stress Level Zero is among my favorite VR game studios, and I believe among the most important in the industry. Their Marrow physics technology totally changes how users interact with virtual environments, making the virtual reality experience more intuitive and usable, two properties that VR software too often lacks. The promise of their most recent game, Bonelab, was one of a modder's paradise that would give those so inclined the tools necessary to create content in the Marrow engine. Nearly 2 years after launch, many of these vital tools necessary to make complicated mods for Bonelab are not in the base SDK. Although Spawn Force, Zone Aggro, and Impact properties have been added to the SDK after a long public hiatus, more powerful tools like base SDK grips and scripting have not been publicly implemented as of now. I've been frustrated by this lacking SDK, so I've made my own VR physics substrate, which I'll tell you all about. Kind of like Marrow, but certainly more primitive. I've removed my skin to show you the most fundamental part of the VR physics rig. Later, we'll get into the more visually appealing aspects of the rig, but it all starts with this primitive construct. This rig must be able to approximate the location of the player's body with colliders, simulate the mechanical action of feet, and actually move itself around in a virtual environment. Starting with movement and its problems, we can't just translate the rig directly, because that's not physics. And we also can't directly apply forces to the rig, because then the player would be able to fly in midair, which isn't quite right. So instead we use a rotoball to approximate the mechanical action of walking, but more smoothly. Real, physical legs would bob the viewport up and down, likely causing motion sickness for any of the weak-stomached. This is a sphere with a high-friction material that can rotate in any direction, and traverse almost any terrain. And by adjusting my joystick, I'm telling it to rotate a certain amount in a certain direction. When I move this rotoball, I'm also moving my whole frame of reference. If this were not the case, I would move and my controllers would stay put like this. And that's no good. It's akin to being in a vehicle on the road. My head, my body, my controllers all move with the rotoball, but I'm still able to move my controllers within this frame of reference. Joystick locomotion is, of course, only one half of the VR movement equation. Movement of the player's headset must also be accounted for. And here we run into a problem. If we are to move forward with our head, we need to move the rig forward as well. But if we move the rig forward, we also move the head forward. So we have a sort of double movement problem. And the solution is to keep the camera glued to the rig. Instead, we move the rig in proportion to how far the real-world headset has moved via the rotoball. The equation is the distance the headset has moved divided by 2πr, the rotoball circumference, to get the number of rotations the rotoball should spin, for all movement must come through the rotoball. You may also notice this movement is quite rapid, and I can tell you it's accurate to my real-world movements, even if I move quickly in my room. This is only possible with a PID, a proportional integral derivative device. The letter P in PID is used for proportional, which is usually some sort of error or distance. Derivative is usually the change in error or distance over the change in time, and integral is the total change in error over all of time. Let's say we have a drone floating in the void, and we have an arrow that points to where we want the drone to be. If we have an arrow above the drone, we want the drone to have a force to go up. The distance between the drone and the arrow is the error, and proportional is the value that represents that error and eventually is turned into a force that goes up into that point. But we'll find, if we do that, that the momentum at this point will take the drone above where it should be, and it will overshoot its target and it will oscillate endlessly. To fix this, we introduce a new value called derivative, which is change in distance, or error, over change in time. And what this should allow us to do is slow down as we reach this point. Derivative increases as the proportional starts speeding up, and eventually derivative should take over proportional and remove all of the momentum that the drone has, eventually leading us to smoothly reach our desired destination. Although we have removed one variable that would usually be present, and that's gravity. To counteract that, we need integral, which is used usually for forces like gravity, which are constant forces that operate on the drone or any other system you have. And the integral is calculated by adding up all the error that has happened in the past, usually to some limit, and eventually that integral should match gravity, so that it counteracts it in the long run, and eventually we reach some sort of equilibrium where there is no bobbing and it smoothly and eloquently reaches its destination. The rotoball PID is more complex as it has two dimensions around which it can rotate, the X and Z axis. Each axis is broken into a separate PID and has forces applied to it uniquely. Both the joystick and the headset feed into this PID. All this combined allows for smooth movement without overshoot or jitter, and a degree of accuracy that should ameliorate motion sickness. The construct you see before you is made of 5 pieces, and thus is referred to as a heptabody. A heptabody is used in both Boneworks and I believe Bonelab, although there are some minor differences between what I've made and the heptabody in those, like the missing torso. They are fundamentally the same. Starting at the very bottom, we have the anchor, which all of the body parts, for the most part, are connected to. This anchor is frozen on the X and Z axis, which allows the player to only move around the Y axis. If that were not the case, then you'd have some sort of 6 degrees of freedom rig, which I believe SLZ are planning on adding at some point in the future. But for now, it's much easier to configure something that's frozen on the 2 axes. What's directly attached to this anchor is the hip, which is around the top of this green capsule you see. The joint between this hip and the anchor is actually what allows for jumping. If I am to press a button to constrict the legs and then release it, it adds a force into the ground which pushes the rig up, just as in real life with bending your legs and then pushing off the ground to jump, which makes it very physically based. The hip height is calculated with a ratio times the player's height, and then there is a little bit of Pythagorean math, which brings us to the head. The distance between the head and the hip has to be constant for what we'll get to later with the rest of the body. Your a squared plus b squared equals c squared, and you can calculate a distance based off of how much the player is crouched and how far the head is forward, and that goes into the height of the hip as well. Going back to the bottom, we have the rotoball, which you are already familiar with, or at least you should be, and the buffer above it. If this buffer were not there, the player would kind of bounce along vertical objects that it gets near, which certainly isn't ideal because it's unrealistic and it doesn't feel very good for the player. I've put on my skin to show you the rest of the physics rig. Each of my limbs are constructed out of capsules. The rig I made uses an active ragdoll to give each of these capsules, and thus my body, a muscular power. An active ragdoll is a ragdoll, which is a construct of primitives like capsules and spheres jointed together, that is then animated with a force, a rotation force, at every joint to simulate muscle. That's what the Nullmen in Bonelab use to be physically animate themselves. That means that before forces can be applied to the active ragdoll, the ideal state of the limb's rotation must be calculated, which is what this guy right here is. The problem with him is we only have 3 points of tracking, that being the head and the hands. There are 2 to 3 methods of calculating these ideal states. The most obvious solution, which is the one Boneworks uses, is called inverse kinematics, which uses math to figure out the rotation of limbs to get from one start point to an end point. In this instance, the head to the hands, through the neck, clavicle, brachium, and forearm. The other solution, which is the one Nimso talks about in this video, uses the physics engine, where either ends of the limbs are jointed to invisible controller and head points. It's similar to how a marionette puppet works in real life, with the strings and the possessor. Beyond that, certain headsets support body trackers, maybe inside-out body tracking, and some people even use Xbox Kinects to gather bodily information with significantly more ease. But not all headsets have body tracking, so a developer must have a solution for the lowest common denominator, which is currently most people. I'm using the marionette method along with proper joint constraints and a little help to get my calculations. It's actually sort of primitive compared to what Nimso or SLC has, which is great because it's easier to set up. Once the calculations are gathered from this guy over here, the rotation information is set to each physical limb on the body. And then a parallel configurable joint on the rig is set to the ideal rotation, which uses a spring to achieve that rotation physically. This body is a bit strong, but it certainly achieves the intended effect. Each part of the upper body, even the elbows, can push against objects with force, which is really nice. I hope you found this video interesting. VR physics, I believe, are the future of much of VR, and really use the medium to its fullest extent. I find them quite interesting as there are a fair few moving parts, although in this video I didn't include other mechanics like grips and animation, nor did I explain how multiplayer functionality works for physics VR, so I'll likely make a video on those in the future along with other VR physics implements. So look out for those in the future. Have a blessed day.